The name of this video is Vector Poisson. In this video, in fact, we want to investigate a similar equation as Poisson equation for the electrostatic field, but in the case of the magnetostatic field, where things get more complicated because we need to deal with vectors such as the vector potential A. So in general, we know that Maxwell's equations in a differential form, case 1, for the magnetostatic field B tell us that the divergence of B clearly is equal to 0 because B is solenoidal. And this, as we know from a previous video on vector potential, implies that B can always be rewritten as the curl of a vector potential A. In addition, we know Ampere's law tells us that the curl of B, which by substituting this expression here, can be eventually rewritten as the curl of A, is equal to mu naught times J in differential form case 1. So now the idea is, what do we do? How do we manipulate this quantity here? The curl of A. Well, first of all, we need to recall from vector calculus an important identity which tells us that the vector Laplacian of a vector field A is given by the gradient of the divergence of A. The divergence of A is a scalar. We feed the scalar to a gradient, gives us a vector. This is the vector Laplacian, and minus the curl of A. Now, as we already know, among all possible infinite A's which I can associate with the vector field B, I can always choose one such that the divergence of A is equal to 0. I need to choose a proper bar phi naught, as we've seen in the previous video. So I can always choose among the infinite A's one which is also solenoidal. And so when I plug this back in here, clearly this quantity here goes to 0. And so the expression just tells us that the vector Laplacian of A is equal minus the curl of A. And so the curl of A is equal minus mu naught J. So eventually down here we can write that the vector Laplacian of A can be written as minus mu naught J. Now, this one should remind you something. Well, it should remind you of the shape of Poisson equation, which in the electrostatic case was nothing but, if you remember, from one of the first weeks of this course, we know that the scalar Laplacian of, let's call it V, to be consistent with the notation we used in the beginning of the course, of V is equal to minus rho, so in this case a scalar, divided by epsilon naught. This is Poisson equation for the electrostatic field, well, for the electrostatic potential. This is a vector form of that, if you want. In fact, since this is a vector, we can rewrite it as the three components in a Cartesian coordinate system: the scalar Laplacian of the x component, so now it's a scalar, I remove vector here, equal minus mu naught, the x component of j, the scalar Laplacian of the y component equal mu naught with a minus of jy, and finally the scalar Laplacian of az equal minus mu naught jz. Okay, so I just rewrote this equation in its own three components, three terms in a Cartesian coordinate system. All right. So now suppose that. So let us suppose that the current density J is limited in space. And this means that A goes to 0 at infinity. Okay, so under these conditions, same equations have same solutions. So each of these three equations is three of them, but each of them is exactly like one of those equations. The only difference is that instead of having 1 over epsilon naught, we have mu naught. And so we already know that one of these solutions is a Colombian type electrostatic potential, and so each of these x, ax and ay and az is also a Colombian type result. Same equations, same solutions. And so we obtain, very simply, that ax at an observation point capital P is given by, instead of 1 over 4 pi epsilon naught, mu naught divided by 4 pi, volume integral, in the region capital omega where jx at q is defined, instead of rho, now we have jx, divided by rqp dv. And similarly, we obtain the same expression, a similar expression for y and for z. I will only write the one for y, and I let you write down the one for z, which clearly is also a Colombian type solution. So this would be jy of capital Q divided by rqp in dv. And the same thing again for az. And I'll let you do that. All right. This set of equations can be rewritten as a single vector equation that is a vector at the observation point capital P equal mu naught over 4 pi volume integral in the region capital omega space of, in this case, I sum up all the components of J, so I obtain J vector at the source point where the current is defined, divided by RQP dV. This is a beautiful result where we have three terms, three components, each of which is of Colombian type, is a Colombian type potential, okay? Stemming from a vector Poisson equation, if you want, as we wrote it down here. Of course, in the case of limited distributions, as soon as somebody gives you, what do they give you in nature? In nature, nature gives us J. So from J, we can do this integral, obtain A. And then finally, in order to solve the problem of B, of course, we just said that B is equal to the curl of A, which we're going to use in order to find the so-called Biot-Savart law, or more generally, Laplace elementary equation, in the next upcoming video. So you do this from this, and you obtain, of course, B, as expected. Now, the key to all this, let's summarize it here. Vector Poisson. So we begin with the Maxwell equations for the magnetostatic field B in differential form case 1. We know that we can define a vector potential, and among all possible vector potential, one which is also solenoidal. Therefore, by means of this vector calculus identity, we can find out the vector Poisson equation, which is three Poisson equations like the one in electrostatics. Under these conditions, we know that each of these solutions is Colombian type, like that. But now mu naught is in the numerator instead of in the denominator epsilon naught. We can sum them up as a vector, do the curl of A, obtain B. The key is the following, one of my favorite ways to solve problems in physics. Same equations, same solutions, which in fact is a sentence from Feynman. And in Phys 342, we will extensively use this concept here in the framework of the vector potential A in order to solve a number of problems by remembering solutions from the electrostatic case. That's it.